what are you going to basically be doing this semester could be represented quickly by this schematic here. Once again, we've got the VBC, which could be these Lego pieces right there. The thymine we can represent like these guys right here, other Lego pieces. And the reaction that you're running this semester is simply taking these two guys, clicking them together, and making VBT. Let's do it again. Oh, there's a VBT. The same polymerization reaction could work, in this case, by linking VBTs together. So this polymerization is simply taking the two VBTs, clicking that would be a dimer of VBT, or something that looks like this, where this group is the thymine unit. Let's go back to our presentation. So now if we want to put both antibacterial functional groups as well as cross-linking functional groups onto a polymer backbone, all we have to do is simply take two different monomers, here the VBT and the VBA, and run the polymerization reaction. Schematically, how this works is quite simple if we go back to our Lego. So one reaction we'll be doing, or could do, is making VBA. So here's the VBA we made before, and here are the two VBTs we just made. And so if we were to make now not just a polymer, but here we have a copolymer because we're working with two different monomers. And we link these together. We might take one of each. There's a dimer, can link another. There's a trimer, and let's put this one over here. Now that's a tetramer. You can put this guy with maybe this one and start a different chain, and maybe this one could go here and form a different chain. But now we made two polymer strands out of those units, and these are both copolymers. You can see the ratio can differ between the VBA. This has two VBAs and one VBT. This has three VBAs and one VBT. So the goal of this semester will be to efficiently prepare and synthesize VBT so that we can do this copolymerization to make a polymer that is both antibacterial as well as cross-linkable. This is a schematic of how the cross-linking can actually happen. When two VBTs from neighboring chains, this is water-soluble, this is a water-soluble polymer chain, here's another water-soluble polymer chain. When the two VBTs are next to one another, if we shine light on them, you can actually have a dimerization occur. Oh, there's a cross-link. So now this polymer is actually linked to this polymer, and this has a much higher molecular weight and would be less soluble in water. If we shine more light, the second thing, another link can happen. Now all three of the chains that you see on the board are all linked together and form one polymer network and is much less water soluble. So last year we started working with the literature procedures for the synthesis of VBT, which involved VBC and thymine itself, and we got a lot of research results. We discovered how to recover starting material. We figured out that the procedure was pretty flawed and yielded very low yields of VBT. We also were able to the students developed a very successful method to follow the reaction. The other thing we figured out was that the VBC was only 90% pure, so 10% of our starting material was already not what we wanted to start with. We discovered that the main impurity in the reactions have RF values lower than the starting material VBC, but higher than the VBT, so we had to figure out a way to get rid of these. And we tried to figure out how to shorten the reaction time, but it wasn't easy to do. The reaction itself was also very intensive, it required many steps, and it wasn't very efficient, so it took a long time to isolate the product. One advance that took place in the research lab, Milo Williams figured out that we could isolate sodium thymine, which is actually a material we were making during the reaction. We weren't isolating it beforehand. This had a major result in that we can now modify the procedure to take thymine, make the salt, the sodium thymine salt or sodium thymine, and then do the reaction with VBC. And 225 studied this reaction last semester, starting with sodium thymine, reacting with VBC to make the VBT, and we were able to do this successfully in 4 hours. You are going to start by reproducing these results this semester to prove that we can actually do this. Here's a procedure that you can look at later. The techniques you're going to learn this semester or next are shown on this slide. You can see many of the techniques will be in 114, but be reinforced later also in 225. And this is the main goal that you should take from this. We're using this research project to show you this entire range of organic chemistry techniques. And so we want you to be able to learn each of these techniques so that you can apply them later to other research projects. And that's your main goal in this year's course. The goals for the research project, Professor Lavoie will cover shortly. So we have main goals for the research project, but I'll save that for another time and update you as the semester progresses so that you can see where we are.